What does it really mean to build a universe inside a computer? Not a video game, not a swirling animation of stars, but the actual physics. The kind a theorist would chalk onto a board, running inside a machine chilled to a hair above the coldest temperature that can exist. Not long ago, physicists did exactly that. On one machine, they say they opened a tunnel through space itself. On another, far larger one, they watched the first flicker of how our universe might end. For a while, it looked like the most extraordinary stretch of physics in a generation. And then a quieter, more unsettling question began to surface behind the headlines. A question that turns out to sit underneath this entire new era of science. When a machine is built to compute the very things we cannot, who or what is left to tell us whether its answer is real? Make yourself comfortable, subscribe if you haven't already, and stick around, because the answer to that question reaches far beyond the two machines at the center of tonight's story. Let's begin. Part 1. The floor that might be a ledge. Right now, as you listen to this, you're sitting on something you have always assumed is solid. Not the chair, not the floor, not the ground under the building. Something further down than any of that. You're sitting on the laws of physics themselves, the fixed rules that decide how every atom in your body holds together, and you have spent your entire life trusting that those rules are permanent. That trust is so complete that you have probably never once thought about it. And yet there is a quiet idea in physics, worked out carefully by serious people over the last 50 years, that says this trust might be the most fragile assumption you have ever made. The idea goes like this. When physicists talk about the universe being stable, what they really mean is that it has settled into a low point, the bottom of a valley, a place where it can rest without rolling anywhere else. Picture a marble dropped into a bowl. It rattles around for a moment, loses energy, and comes to rest at the lowest spot it can find. That resting place is what gives the marble its calm. The universe, in this picture, is the marble, and the valley it rests in is what physicists call the vacuum, the baseline state of empty space when everything else has been stripped away. For 100 years, we have assumed our universe found the lowest valley there is and settled there for good. It helps to be precise about what physicists actually mean by that word, vacuum, because the everyday version of it is misleading. When most of us hear vacuum, we think of emptiness, of nothing at all, of the void you would find if you removed every last particle from a sealed box. But to a physicist, the vacuum is not nothing. It is the lowest energy state of the fields that fill all of space, the quietest configuration those fields can settle into. And those fields are everywhere, even in the emptier stretch of intergalactic space, humming along at their lowest setting. Empty space, in this view, is not a blank stage on which physics happens. It is a thing in its own right, with properties, with structure, with a particular energy that it has chosen to rest at. When we say the universe might be in a false vacuum, we are not talking about the emptiness between the stars. We are talking about the resting state of reality itself, the baseline that everything else is built on top of. That is why the marble in the bowl is such a useful picture, and why it is also a little too comforting. A marble resting at the bottom of a bowl is genuinely stable. Tip the bowl gently and the marble rolls back. But now imagine the bowl itself is sitting on a narrow shelf, and just over the lip of that shelf the floor drops away to a lower level you cannot see from where the marble sits. The marble feels perfectly at rest. By every local test it is at rest. It could sit there, undisturbed, for an almost unimaginable span of time, and yet it is not at the true bottom. It is one nudge, one rare and random fluctuation, away from discovering that the floor it trusted was a ledge after all. The unsettling genius of the false vacuum idea is that stability and doom are not opposites here. The same calm that lets the marble rest is the calm that hides the drop. But here is the unsettling possibility. What if the valley we are resting in is not the lowest one? What if, somewhere lower, there is another valley, a more stable arrangement of the laws of physics, and our universe simply has not found its way down to it yet. In that case, the calm we feel is a kind of illusion. We would not be resting at the true bottom. We would be perched on a ledge partway down the mountain, a ledge that looks for all the world like solid ground, while a lower and more permanent floor waits somewhere beneath us. Physicists have a name for the ledge we might be standing on. They call it a false vacuum, and they call the lower valley, the one we may not have found, the true vacuum. If that picture is correct, then something can happen that should keep you awake at night. Somewhere out in the universe, in a patch of space no one is watching, our false vacuum could find a way to slip down into the true vacuum. It would not happen gradually. It would happen through a quantum event, a tiny region of space spontaneously flipping from the ledge we live on into the lower valley underneath. The instant it flipped, that region would become a bubble of truer, more stable reality, sitting inside our own. And that bubble would not politely stay where it formed. It would begin to grow. I want you to sit with what that growth would actually mean, because it is stranger and quieter than any disaster you have ever imagined. Imagine you're standing in your kitchen on an ordinary evening. The light is on. The window shows the last colour of the sky. Somewhere, unimaginably far away, or perhaps not so far, a bubble of true vacuum has formed, and its surface is rushing outward in every direction at very nearly the speed of light. Inside that bubble, the constants of nature are different. The strength of the forces that bind atoms together is not what it was. Chemistry, in any form you would recognize, simply stops working. Matter as you know it cannot exist inside the new region, and because the wall of the bubble is moving at almost exactly the speed of light, the light from its approach arrives at the same moment the wall itself does. There is no glow on the horizon. There is no warning shape in the sky. The last instant of the world you know, and the first instant of the new region arrive together, in perfect silence. You would never see it coming. No one would. There would be no pain, no flash, no chance to turn your head. One moment the kitchen, the window, the evening light. The next moment, nothing that could even be called a moment, because the thing that measured moments would be gone. Now, before this becomes unbearable, let me steady the picture with something important. This is not a prophecy. No one has seen a bubble of true vacuum. No one knows for certain that the lower valley even exists. What we have is a piece of mathematics, first written down carefully in the late 1970s by a physicist named Sidney Coleman, that says the scenario is possible and tells us, in precise terms, how it would unfold if it were real. For decades that was all it was. A line of reasoning on a chalkboard. A frightening sentence in a research paper that most people would never read. Something you could argue about over coffee and then walk away from, back into a world that felt, for all practical purposes, completely solid. And walk away from it we did for almost 50 years, which is the part that makes the idea so easy to underestimate. It is not a new theory, dreamed up last year to chase headlines. It is an old and patient consequence of equations we already trusted, sitting quietly in the literature the whole time, neither proven nor dismissed. Physicists are oddly comfortable with this. They can hold a possibility like the end of everything at arm's length, treat it as a technical question about the shape of a potential energy curve, and go home for dinner without a tremor. There is a kind of professional calm to it that the rest of us, hearing the idea cold, do not share. The calm is not denial. It is the recognition that the timescales involved are so enormous, and the uncertainties so wide, that the idea changes nothing about how you should live or what you should fear on any human horizon. What I find quietly remarkable is that this same arm's-length idea, the one physicists could discuss so calmly, is the thing a team decided to build a working model of. They did not set out to terrify anyone. They set out to take a piece of mathematics that had floated untested for half a century and finally connect it to something they could measure. That is the whole impulse of this story, the urge to drag the untouchable into reach and it is worth holding on to because it is also exactly the impulse that gets us into the trouble we will spend the rest of this night exploring. The reach for the untouchable is glorious. It is also where the hardest questions about trust begin. What changed? And the reason you're hearing this story tonight is that in the early part of 2025, a team of physicists did something that had never been done before. They did not wait for the universe to show them a bubble. They built a small one. Not a real bubble of true vacuum, not a danger to anyone, but a working model of the exact mechanism Coleman described, running inside a machine. They took a quantum computer, one of the strangest and most powerful kinds of machine humanity has ever made, and they tuned it until it behaved like a slice of a false vacuum. Then they pulled the trigger and they watched the bubbles form. For the first time in the history of our species, the process by which a universe could end was unfolding somewhere a human being could actually observe it, measured, recorded, and held still long enough to study. And that is where this story begins to turn into something larger than a single experiment. Because once you have a machine that can simulate the end of the universe, a quieter and far more disorienting question begins to form behind the obvious one. The obvious question is whether the universe will really end this way. The quieter question, the one that will follow us through everything that comes next, is this. When a machine shows you the end of the universe, how do you know it is telling you the truth? Hold on to that question. We are going to need it. Part 2. They built one in a ring of wires. The machine that did this is not the kind of computer sitting on your desk, and it is worth slowing down to understand what it actually is, because the strangeness of the result depends entirely on the strangeness of the device. The team used something called a quantum annealer, built by a company named D-Wave, and the particular one they worked with was installed at a place called the Jülich Supercomputing Center in Germany. An ordinary computer stores information in bits, tiny switches that are either on or off, 1 or 0. A quantum computer stores information in quantum bits, usually shortened to qubits, and a qubit is allowed to do something no ordinary switch can do. It can exist in a mixture of on and off at the same time, a fragile in-between state that only survives if the qubit is kept exquisitely isolated and brutally cold. The machine in Germany held 5,564 of these qubits. To give you a sense of how many that is, the most famous quantum computing experiments of the previous decade ran on a few dozen qubits at most. 5,564 is not a small step up from that. It is a different order of scale entirely. It is worth pausing on what kind of quantum computer this actually was, because not all of them work the same way, and the difference matters for the rest of the story. The machine in California that we'll meet a little later, the one tangled up in the wormhole claim, was what physicists call a gate-based quantum computer. It manipulates its qubits with a sequence of precise operations called gates, the quantum cousins of the logic steps inside an ordinary processor, applied one after another like the moves of a careful dance. The machine in Germany was a different beast altogether. It was a quantum annealer. Instead of choreographing a sequence of individual moves, an annealer sets up a terrain of energy, a kind of mathematical terrain with hills and valleys, and then lets the whole system of qubits settle naturally toward the lowest point it can find, the way water finds its level or a ball rolls downhill. You do not tell an annealer each step to take. You shape the terrain, release the system, and watch where it flows. That turns out to be a natural fit for a problem like the false vacuum, because the false vacuum is, at bottom, a question about landscapes and where a system settles within them. By tuning the strength of every connection in the ring, the team sculpted an energy terrain with a higher valley, the false vacuum, and a lower one, the true vacuum, and then they watched the system try to find its way down. The qubits themselves were loops of superconducting wire, and superconductivity is its own small miracle. When certain metals are cooled far enough, their electrical resistance does not just shrink, it vanishes completely, and current can flow around a loop forever without losing a drop of energy. It is in that frictionless, resistance-free state that the loops begin to obey quantum rules at a scale large enough to wire together by the thousands. And the hardest part of all is keeping that quantum behavior alive, because the quantum world is shy. The moment a qubit is disturbed by stray heat or a passing vibration, its delicate in-between state collapses and the computation dies. Physicists call the survival of that fragile state coherence, and coherence is the currency of the whole enterprise. Holding more than 5,000 qubits coherent long enough to watch bubbles form is a feat of engineering as much as physics, a matter of shielding and cooling and patience, and it is the quiet reason this experiment could happen at all. The qubits in this machine are made of loops of superconducting wire, cooled until they lose all electrical resistance, chilled to a small fraction of a degree above absolute zero, which is the coldest temperature that can exist, the point where all heat has been removed. At that temperature, the loops of wire start to behave according to the rules of quantum mechanics rather than the rules of everyday objects, and that is what lets them serve as qubits. The team arranged these thousands of qubits in a ring, a closed loop, and then they did something clever with the connections between them. They tuned the strength of every link, the way each qubit pushes and pulls on its neighbours, until the entire ring of wires behaved like a physical system that physicists already understood very well on paper. That system is called the Ising model, and you do not need to follow the mathematics to follow the story. The Ising model is best thought of as a kind of toolkit, a flexible set of rules that physicists can bend to imitate many different situations. Tune it one way, and it describes a magnet. Tune it another way, and it describes a different material entirely. What this team did was tune it so that the ring of qubits behaved like a one-dimensional slice of a false vacuum, the exact unstable ledge that Coleman had written about almost half a century earlier. In other words, they did not just build a powerful computer, they persuaded a powerful computer to pretend, faithfully and in detail, to be a universe perched on the edge of collapse. Then they triggered the transition. They nudged the system so that it could begin to slip from the false vacuum toward the true vacuum, and they watched what happened next unfold in the data streaming out of the machine. And what happened was exactly what the cosmological picture predicted. Bubbles of true vacuum began to form inside the ring. Small ones appeared first, little pockets where the qubits had flipped into the new, lower energy arrangement. Then larger ones formed. The bubbles grew. They pushed outward into the surrounding false vacuum. They ran into each other and merged. The whole shape of the thing, the way the bubbles nucleated and spread and collided, matched the equations physicists had been writing down for decades, without ever being able to test them against anything you could actually watch. Some of these bubbles, by the time they'd grown to full size, contained the equivalent of 300 spin flips, which in the language of this machine means 300 qubits all changing their state together in a single coordinated pattern. 300 qubits moving as one is not a small ripple. It is a large, organized, coherent structure, the kind of thing that is supposed to be almost impossible to maintain in a quantum system, because quantum states are notoriously delicate and tend to fall apart the instant the outside world touches them, and yet the structure held. The whole simulation stayed coherent, stayed quantum, stayed faithful to the physics, for more than a millionth of a second. I know how that sounds. A millionth of a second is not a length of time a human being can feel. It is shorter than the blink you did not notice yourself doing a moment ago. But you have to measure time in the units that matter to the thing you're watching, and for a quantum system at this scale, a millionth of a second is enormous. It is more than 1,000 of the natural ticks of the machine, the intrinsic beats that set the pace of everything the qubits do. 1,000 ticks is long enough to study the dynamics seriously. It is long enough to watch a bubble form, grow, and collide with another bubble, and to write down equations describing every stage of it, and then to compare those equations against the theory and find that they agree. In the strange accelerated world of the qubits, the team did not catch a fleeting look at the end of the universe. They watched it happen slowly with time to spare. There was one more thing they found, and it is the kind of detail that turns a tidy result into a living piece of science. The formation of a new bubble, it turned out, was not an isolated event. A bubble did not simply pop into being on its own, indifferent to everything around it. Instead, the bubbles influenced each other. The presence of one changed the odds and the behaviour of the next. The whole process was collective, a many-handed interaction rather than a series of separate accidents, and the size each bubble reached was set by a tug-of-war between two competing pressures. On one side, there was energy to be gained by converting more of the false vacuum into true vacuum, which pushed each bubble to grow. On the other side, there was an energy cost to maintaining the surface of the bubble, the boundary between the old reality and the new, which pushed back against the growth. The balance between those two pressures decided how big each bubble became, and that balance is exactly what the standard cosmological account had always predicted. There is something worth savouring in that agreement, because it is rarer and more meaningful than it might sound. For decades, the account of how bubbles of true vacuum would form and grow was a piece of pure theory, a set of equations derived from first principles with no way to check them against anything real. Theorists believed the equations because the reasoning was sound, not because anyone had ever seen the process happen. To then build a system, however simplified, and watch bubbles nucleate and grow according to that same competition between volume and surface, is to see a long untested prediction step out of the chalkboard and into a measurement. That is the ordinary sturdy way science is supposed to work, theory meeting observation and the two shaking hands. It is precisely the kind of confirmation the wormhole experiment never quite got, and the contrast between the two is a quiet thread running under this whole story. The machine, in other words, did not just produce bubbles, it reproduced the precise logic by which a real universe would decide the fate of its own bubbles. There is, of course, a catch, and the team was the first to say so plainly. Their simulation ran in one dimension. The bubbles formed along a line, a single ring of qubits, while the universe we actually live in has 3 dimensions of space. So what they watched is not a literal preview of how false vacuum decay would tear through our cosmos. It is a faithful model of the mechanism in a stripped-down version of the problem, a one-dimensional sketch of a 3-dimensional nightmare. The team noted, almost casually, that 3-dimensional versions are possible on the same kind of hardware with more work, and that is where this corner of physics is now heading. But even the one-dimensional sketch was a first. No one had ever watched this mechanism happen anywhere, in any form, at any scale, until a ring of frozen wires in Germany showed it to them. The remarkable part is not that the bubbles were small, or that the model was simple. The remarkable part is that the end of a universe, a process we had only ever argued about in the abstract, had finally been dragged into a place where human beings could stand and watch. And the moment you can watch something like that, you are forced to ask whether you can believe what you're seeing. Part 3. Inside the Cold. To really understand what these physicists did, I want to take you inside the machine, down past the headlines and the diagrams, into the cold where the work actually happens. Come with me for a moment and let the rest of the world fall away. You're standing in a quiet laboratory, and in front of you is a structure that does not look like a computer at all. It looks like a chandelier hung upside down, a tower of gleaming golden plates and coiled tubes descending in tiers, each level colder than the one above it. This is the refrigerator that holds the quantum machine, and it is doing something almost unbelievable. It is pulling heat out of its own centre until the temperature there falls to 1/100th of a degree above absolute zero, colder than the empty space between the stars, colder than anywhere in the natural universe we have ever measured. At that temperature, atoms barely move. The faint trembling that we call warmth has almost entirely stopped, and in that profound stillness, down in the coldest tier, sits a ring of superconducting loops, 5,564 of them, waiting. Now watch what happens when the experiment begins. The whole ring has been tuned to sit on the ledge, the false vacuum, balanced and uneasy. For an instant nothing moves. Then, somewhere along the ring, a handful of qubits flip, A small region lets go of the ledge and drops into the lower valley, and a bubble of true vacuum is born, no larger at first than a few links in the chain. You watch it spread. The flip propagates outward to neighbouring qubits, the bubble widens, and now it is dozens of qubits across, now 100, now approaching 300, all of them changed over to the new state and holding that new state together in a single coherent pattern. Nearby, a second bubble appears, then a third, and you can see them feeling each other across the ring, their growth subtly shaped by one another's presence. They expand toward one another, they touch, they merge, and all of it is happening in a silence so complete and a cold so total that the only sign anything has occurred at all is a stream of numbers flowing out of the machine into the warm room where the physicists are sitting, watching the end of a small universe scroll past on a screen. Stay in that cold a moment longer with me, because there is something worth noticing about the strangeness of the scene. The refrigerator that holds the machine is built in tiers, each one a stage in a relay of cooling, each colder than the last, handing the heat upward and away until the bottom stage reaches that final 100th of a degree above the absolute floor of temperature. Gold-plated plates, coiled tubes, the whole apparatus gleaming and still. It does not look like a window onto the end of the universe. It looks like a sculpture or a strange chandelier hanging silent in a quiet room. And that mismatch between the enormity of what is being modelled and the smallness and stillness of the thing modelling it is part of what makes this moment in science so disorienting. For all of human history, the questions of how everything begins and how everything might end have belonged to a category we treated as untouchable. They were the province of philosophy, of religion, of late-night wondering. You could think about the end of the universe, but you could not do anything about it, could not measure it, could not bring it into a room and set instruments on it. It lived at a distance no telescope could close, in a future no clock could reach. And now, a version of that question has an address and a temperature. It sits in a building you could drive to, cooled to a number you could write down, producing data a graduate student can read off a monitor at 2 a.m. The end of the universe has been miniaturized, not as a threat but as an object of study, and a human being can pull up a chair and watch its machinery turn. That is either the most reassuring thing in this entire story or the most unnerving, and which one it is depends entirely on whether you trust what the machine is telling you, which is exactly the question we are circling toward. Step back now, out of the cold, into the ordinary light of the laboratory. What you just watched was not the universe ending. It was a model, a one-dimensional sketch running in a ring of frozen wires. But it was a faithful model, faithful enough that the equations describing it match the equations describing the real thing. And there is something quietly staggering about that. For the entire history of human thought, the largest questions, the ones about how everything begins and how everything might end, have lived in a place we could never reach. We could think about them, we could write them down, we could not touch them. And now, for the first time, one of those questions has been brought down out of the abstract and into a machine you could walk up to and put your hand against the cold housing of. The end of the universe, or at least its mechanism, has an address. It is in a basement in Germany, 100th of a degree above the coldest possible temperature, and human beings can go and look at it whenever they choose. Try to sit with how recent that is, in the long story of our species. For tens of thousands of years, human beings looked up at the night and asked what the lights were and how it would all end, and the only honest answer was silence and guesswork. We built myths to fill the gap, then philosophy, then, slowly, a science that could at least measure the lights even if it could not touch them. The end of the universe stayed firmly in the category of things you could only reason about from a distance, never approach, never set an instrument upon. Across all those generations, no one could have imagined that the mechanism of cosmic collapse would one day be available for inspection in a cooled box you could photograph. And yet here we are, and the very ordinariness of it is the strange part. There is no thunder in that laboratory, no sense of occasion that matches the size of the question. There is a hum, a stream of data, a few tired researchers, a cup of coffee going cold beside a keyboard. The most enormous idea a mind can hold has been rendered small enough to fit into an afternoon's work. That compression of the cosmic into the laboratory is one of the quiet triumphs of this era of physics. But it carries a hidden cost that the rest of this story is about, because the moment you can hold the end of the universe in a box and read its behaviour off a screen, you have to start asking whether the screen is telling you the truth, or only telling you what you built the box to say. That alone would make this one of the strangest experiments of our time. But the strangeness is only beginning, because the closer you look at what it means to watch a thing like this inside a machine, the more you start to wonder what watching even means anymore. Part 4. Why this is not science fiction. At this point, a reasonable person might object, and the objection is worth taking seriously. All of this talk about false vacuums and bubbles that end the world sounds like the premise of a film, the kind of idea a screenwriter invents because it is frightening, not because it is true. So let me be clear about where this comes from, because the unsettling thing about false vacuum decay is not that it is wild speculation. The unsettling thing is how conservative it is. It falls out of the most successful theory in the history of science, almost as an afterthought, and the people who take it seriously are not cranks. They are the same physicists whose predictions have been confirmed to more decimal places than any other set of ideas humanity has ever produced. The story starts with Sidney Coleman, who in 1977 wrote a paper with the almost theatrical title, The Fate of the False Vacuum. Coleman was not trying to scare anyone. He was working out the mathematics of how a quantum field would behave if it were sitting in a state that was stable in the short term, but not truly the lowest available. What he found was that such a field would not stay put forever. Quantum mechanics does not allow for perfect, permanent stillness. There is always a tiny chance, governed by the same tunneling rules that let particles slip through barriers they should not be able to cross, that a small region will spontaneously make the jump to the lower state. And once it does, Coleman showed, that region becomes a bubble that expands, converting everything it touches. He even calculated, in rough terms, how long you might expect to wait for such a thing to happen by chance. The answer he arrived at was something like the lifetime of the universe itself, which is a strange and double-edged kind of comfort. The mechanism Coleman described deserves a closer look, because it is one of the quietest and most patient catastrophes physics has ever imagined. In the everyday world, things change when they are pushed. A ball rolls over a hill because something gives it a shove, but quantum mechanics allows for a different kind of change, one that needs no push at all. A system can simply tunnel, slipping through a barrier it does not have the energy to climb over, appearing on the far side as if by sleight of hand. It is the same effect that lets particles escape from the nucleus of a radioactive atom, and it is governed by chance. There is always some probability, usually fantastically small, that a region of the false vacuum will tunnel through to the true vacuum on its own, with no warning and no cause beyond the dice roll of quantum law. When it does, a bubble is born, and the wall of that bubble carries an enormous amount of released energy, which is what drives it outward at nearly the speed of light. The reason this stopped being a purely abstract worry has a date and a place attached to it. In 2012, at the Large Hadron Collider beneath the border of France and Switzerland, physicists finally detected the Higgs boson, the long-sought particle tied to the field that gives many other particles their mass. Finding it was a triumph, the capstone of a 50-year search, but measuring its mass had a consequence almost nobody celebrated. The Higgs field is precisely the kind of field that can have a false vacuum, and the stability of its current state depends on a delicate balance between the mass of the Higgs and the mass of the top quark, the heaviest particle we know of. When you plug the measured numbers in, roughly 125 for the Higgs and roughly 173 for the top quark, in the units physicists use, the balance lands in that ominous middle zone. Not comfortably stable, not actively decaying. Metastable, sitting on the knife's edge. It is as if we went looking for the foundation stone of reality, finally found it, and discovered it was balanced on its corner. Coleman's reassurance that the weight might be as long as the age of the universe still holds, and the error bars on that estimate are so enormous that the honest answer remains we simply do not know. We probably have an immense stretch of time. We might not. And nothing about our daily lives would ever reveal which. It means the odds of it happening in any given year are staggeringly small. It also means it is not impossible, and that the timescale carries enormous uncertainty in both directions. The honest summary is that nobody knows. We probably have an immense stretch of time, or we might not. For decades, that was where the matter rested. A beautiful and disturbing calculation with no way to connect it to the universe we actually live in. And then particle physics caught up with it in a way that nobody especially wanted. At a machine called the Large Hadron Collider, the enormous particle accelerator buried beneath the border of France and Switzerland, physicists measured the mass of a particle called the Higgs boson, the particle responsible for giving other particles their mass. They found it to be roughly 125 times the mass of a proton in the units physicists use, a number that sounds arbitrary until you combine it with another measurement, the mass of the heaviest known particle, the top quark, which comes in at around 173 of those same units. When you take those two numbers and feed them into the equations of the standard model of particle physics and ask what they imply about the stability of the vacuum, the answer that comes back is not reassuring. The numbers place our vacuum in a very particular region. One physicist described with a carefully chosen word. They call it metastable. Metastable is the word that should give you pause, so let me unpack it. It does not mean stable. It does not mean unstable. It means balanced on a knife's edge between the two, stable enough to last for a very long time, but not stable in the final permanent sense we always assumed. If the measurements had come back a little different, the math would have said our vacuum is solidly stable, the lowest value there is, nothing to worry about ever. If they had come back different the other way, the math would have said our vacuum is actively unstable and should already be decaying. Instead, they came back almost exactly on the boundary, in the narrow zone where the universe appears to be sitting on a ledge after all, a ledge that is high enough to be in no immediate danger, but not the true floor. Of all the values those two masses could have taken, the universe seems to have chosen the one that is most quietly ominous. It is worth saying plainly what it would actually mean for the constants of nature to be different inside a bubble of true vacuum, because the phrase is easy to nod along to without feeling. The strength of the forces that hold an atom together is not arbitrary. It is set by the values that the underlying fields have settled into, the same values that the false vacuum question puts in doubt. Shift them, even slightly, and the delicate arrangement that lets protons and neutrons cling together in a nucleus, that lets electrons orbit in stable shells, that lets atoms bond into molecules, could simply cease to hold. Inside the new region, the rules that make matter possible would be rewritten. There would be no atoms as we know them, no chemistry, nothing that could assemble itself into a star or a planet or a thought. It would not be a place hostile to life in the way a desert or the vacuum of space is hostile. It would be a place where the very preconditions for there being anything at all had been quietly revoked. This is why the calm of the physicists and the dread of the newcomer are both correct in their way. The dread is correct because the stakes could not be larger. The calm is correct because the timescale, as best anyone can estimate it, is so enormous that it touches nothing you will ever experience, and because the estimate itself is so uncertain that it is closer to an admission of ignorance than a prediction. The right posture, I think, is neither panic nor dismissal, but a kind of sober wonder. We live, it seems, on a foundation that is probably stable for longer than the current age of the universe, and possibly not, and we have no way yet to close that gap. To hold that thought without either flinching from it or being crushed by it is one of the stranger exercises modern physics asks of us, and it is the exercise that makes a team want to build a model they can actually watch, just to turn the unbearable abstraction into something with edges. Now I want you to feel the full weight of what this means, because this is the moment where an abstract calculation becomes personal. Every solid thing you have ever known, the chair beneath you, the bones inside you, the ground that has held up every step you have ever taken, is solid only because the laws of physics are currently set the way they are. And those laws, according to our best measurements, may not be locked in place. They may be resting where they are the way a boulder rests on a slope, held by friction and habit but not by any underlying guarantee. The permanence you have always felt in the world, the bedrock certainty that reality is just reality and always will be, may be the single largest illusion any of us carries. The ground under reality may not be a floor at all, it may be a ledge. And the strangest part is that you can know this. You can sit with it tonight, and tomorrow the sun will still rise and the world will still feel solid, because the ledge, if it is a ledge, is a very wide and very old one. We live our whole lives on it without ever feeling the drop, but the drop, the physicists tell us, may be there all the same. This is why the experiment in Germany matters so much, and why it is not science fiction. The team did not invent the false vacuum to frighten anyone. They took an idea that the most rigorous theory we have was already pointing at, an idea that our own measurements of the Higgs boson and the top quark had made uncomfortably plausible, and they found a way to watch its machinery turn. They built a place where the mechanism of the end could be observed without the end actually arriving, and in doing so they gave us something we had never had before, which is a way to study the most final question imaginable as an experiment rather than a fear. But the instant you turn the end of the universe into an experiment, you inherit a problem that has nothing to do with bubbles or vacuums or Higgs bosons. A problem that turns out to sit underneath not just this experiment, but a whole new era of physics. It is the problem of knowing whether the machine is right. And to see why that problem is so serious, we have to leave the false vacuum behind for a while and go back 3 years to a different machine and a claim that for a few weeks looked like the most extraordinary result in modern physics. Part 5. The question. Underneath. Before we go back, I want to plant a question in your mind and let it grow quietly while we travel, because it is the real subject of everything that follows. The false vacuum experiment was beautiful, and as far as anyone can tell it was correct. But ask yourself something simple. How would we know if it were not? How would anyone check? For almost the entire history of science, there has been a clean and reliable answer to that question. An answer so dependable that we rarely had to think about it. You did an experiment, then somebody else, somewhere else, did the same experiment. If they got the same answer, the result was probably real. If they got a different answer, then somebody had made a mistake, and the community went looking for it until they found it. That single rule, repeat it, and see if it holds, is the engine that has driven scientific progress for centuries. The power of that rule is easiest to feel through the times it saved us. Think of the famous episode decades ago, when 2 chemists announced they had achieved nuclear fusion in a jar on a tabletop, at room temperature, a result that would have rewritten the world's energy future overnight. The claim made headlines everywhere, and then laboratories around the globe tried to reproduce it, and could not, and the result quietly collapsed under the weight of its own unrepeatability. The system worked exactly as it was supposed to. An extraordinary claim was made, the community tested it independently, the claim failed the test, and science corrected itself. No one had to trust the original announcement, because trust was never the currency. Reproduction was. That is the immune system of science, the mechanism that lets a discipline made of fallible human beings still converge, over time, on things that are actually true. Now watch what happens to that immune system when you cannot reproduce the experiment in any independent way. If the only machine capable of running your simulation is the one you already used, and there is no second kind of apparatus that can check it, then the immune system has nothing to work with. You're left holding a result that no one can confirm and no one can refute by the usual means. A claim that floats free of the mechanism that normally anchors claims to reality. The partial tools the field has developed help around the edges, Cross-entropy benchmarking compares the statistical fingerprint of a machine's output against what theory expects for small enough cases. Shadow tomography lets you estimate many properties of a quantum state from limited measurements. Randomized benchmarking probes how reliably the individual operations are being carried out. Each is genuinely useful, but every one of them checks a piece, a specific aspect of the device's behavior, and none of them can stand back and certify that an entire large simulation, out past the reach of any classical check, has told you the truth about nature. The tools test the instrument. They do not validate the song it plays. It works for telescopes. It works for particle accelerators. It works for chemistry, for biology, for materials science, for nearly everything where you can build a second copy of the apparatus, run it again, and compare. The whole edifice of trust we have in science rests on the fact that nature does not change its answer, depending on who is asking. But that rule is beginning to break down for quantum simulation, and the reason it breaks down is the very thing that makes quantum simulation worth doing in the first place. Think about why you would build a quantum computer at all. The entire point is to compute something that an ordinary computer cannot. If a regular machine could simulate a false vacuum of 5,000 qubits, or model the full behavior of the system the wormhole team was studying, you would not need the quantum device. You would just run it on a laptop and save yourself the trouble of cooling a chandelier of wires to the edge of absolute zero. The quantum computer earns its existence precisely in the territory where classical computers give up, where the problem is too large and too tangled for any normal machine to follow, and that creates a trap that is easy to miss until you stare straight at it. Suppose your quantum simulation tells you something surprising. Suppose it shows you a bubble of true vacuum forming in a way you did not expect, or a signal that looks like a piece of gravity. How do you check whether the answer is right? You cannot run it on a classical computer to compare, because the whole reason you built the quantum machine was that the classical computer cannot do this calculation. The check you would normally reach for is the one check you are forbidden from using. You're out past the edge of the map, and the instrument that took you there is the only instrument that can read the territory, which means you have no independent way to know whether the instrument is lying. Let me make that trap concrete with a small picture. Imagine you have built a telescope so powerful that it can see a region of the sky no other telescope on Earth can reach, and one night it shows you something astonishing in that region, a structure no one has ever reported. How do you confirm it is real? Ordinarily, you would ask another observatory to point at the same patch of sky and tell you whether they see it too. But in this case, there is no other instrument that can see that far. Your telescope is the only eye that reaches the territory. If the structure is real, your telescope is the hero that found it. If the structure is a flaw in your own optics, a smudge on the only lens capable of looking, your telescope will show you that smudge faithfully every single night and call it a discovery every time. You would have no way from observation alone to tell the difference. You would need someone to take apart the design of the telescope itself and reason about whether it could be fooling you. That is the position quantum simulation has walked us into, and it is worth feeling how new and how strange it is. For most of science, the instrument and the check were separable. You could always, in principle, build a second instrument of a different kind and cross your fingers that the two agreed. Here the instrument is, by its very purpose, the only one that can reach the answer, so the check has to come from somewhere other than repetition. It has to come from understanding the instrument so thoroughly that you can reason about when it would mislead you. Hold that image, the lone telescope and the smudge that looks like a discovery, because in a few minutes you are going to watch it happen for real, not with a telescope, but with 9 qubits and a pattern in the data that an entire field, for a while, mistook for gravity. This is what physicists call the verification problem, and for years it lived quietly in the background of the field, a technical worry that specialists acknowledged and then mostly set aside. It connects to something fundamental about quantum computing that researchers have understood for a long time. Quantum machines are believed to be able to solve certain problems far faster than any classical machine ever could. But confirming that a quantum machine has produced the correct answer is often just as hard as solving the problem would have been in the first place. The same power that makes these machines so valuable is the very thing that makes them so difficult to trust. There are partial tools with names like cross-entropy benchmarking and shadow tomography and randomized benchmarking, and each of them can check some specific aspect of how a quantum device is performing. But none of them offers a general, reliable way to take an arbitrary quantum simulation and certify, beyond doubt, that its output is true. We have built machines that can answer questions we cannot answer ourselves, and in doing so we have partly cut ourselves off from the ability to know when their answers are real. For a long time this stayed abstract, a philosophical itch rather than an urgent problem. Then it stopped being abstract. Then it became the centre of one of the most uncomfortable arguments in modern physics, an argument that played out in public over more than 2 years and ended with a journal doing something it almost never does. And it all started with 9 qubits, a famous chip in California, and a claim that physicists had finally dragged gravity itself into the laboratory. Part 6. The last time we were sure. Go back then to the start of 2022. In a laboratory in Santa Barbara, a small team of physicists was preparing to run an experiment on a machine called the Sycamore processor, a quantum chip built by Google. Sycamore was already famous. 3 years earlier it had been the centerpiece of Google's claim to have achieved something called quantum supremacy, the first demonstration that a quantum computer could perform a specific task no classical computer could match in any reasonable time. It is worth being clear about what quantum teleportation is and is not, because the word carries so much science fiction baggage that it can mislead before the story even begins. Teleportation in this sense does not move matter, and it does not send anything faster than light. What it moves is quantum information, the fragile state of a qubit, from one location to another by using a pair of entangled particles as a kind of channel. Entanglement is the strange thread at the centre of it. 2 particles can be linked so that they behave as a single system, no matter how far apart they are, so that the state of one is bound up with the state of the other. To teleport a qubit, you entangle 2 particles, send one to each side, and then perform a careful measurement that transfers the original qubit's state across the link, with a little ordinary information sent alongside to complete the process. The qubit does not travel through the space in between. It vanishes on one side and is reconstructed on the other. By 2022, this was a known and repeatable trick, performed in laboratories around the world. It was not the teleportation that made the experiment famous. What made it famous was the costume the teleportation was wearing. The team had arranged their 9 qubits so that the 2 sides of the system were not just any entangled clouds, but clouds described by the special model that, through the holographic lens, looks like gravity. So when the qubit crossed from one side to the other, the team could describe that crossing in 2 languages at once. In the plain language of quantum information, a qubit had been teleported, nothing exotic. But in the language of the holographic dictionary, that same event read as a particle falling into one black hole, travelling through the throat of a wormhole held open by a pulse of negative energy, and emerging from a second black hole on the far side. Same event, 2 descriptions, and the whole drama of the next 3 years would come down to a single question about those 2 descriptions. Were they truly equivalent? The glasses genuinely on, so that the teleportation really was a window onto gravity? Or had the model been shrunk so far that the gravitational description had quietly stopped applying, leaving only the ordinary teleportation wearing a borrowed costume that no longer fit? The chip carried 53 superconducting qubits in total. But for this new experiment, only 9 of them would actually do the work. 9 qubits, and a circuit so small by the standards of modern computing that you could almost hold the whole thing in your head at once. The team was small and unusually heavyweight, the kind of group that makes other physicists pay attention. There was Daniel Jafferis from Harvard, who had spent years working on the theory that made the whole attempt possible. There was Maria Spiropoulou from Caltech, who led the effort. There was Joseph Licken from Fermilab, the Great American Particle Physics Laboratory. There was Alexander Zlokaper, who was a graduate student at the Massachusetts Institute of Technology at the time and who would do much of the crucial work of shrinking the problem down. And there was Hartmut Neven, who runs Google's quantum computing group. They had been building toward this for a long while, and in January of 2022 they finally ran it. The long while is worth dwelling on, because it tells you this was not a stunt thrown together for a press release. The theoretical groundwork stretched back years, to the moment physicists first realized that the holographic correspondence might let them do more than describe a wormhole on paper, that it might let them route a signal through one. The key insight, that two entangled quantum systems could be coupled in a way that, through the glasses, looked like the negative energy needed to hold a throat open, had been worked out and refined and argued over long before any chip was cooled. Then came the harder labour of translation, of taking that elegant idea and figuring out what an actual quantum processor would have to do, gate by gate, to enact it. Years of work sit behind the single sentence. In January they ran it. That history matters for how we judge what happened next, because it would be a mistake to paint these as careless people chasing a headline. They were serious physicists pursuing a genuinely beautiful idea, one that, if it had held up in the strong form they first described, would have deserved every bit of the attention it received. The disappointment that followed was not the disappointment of catching a fraud. It was the subtler ache of watching a beautiful idea turn out to be true in a smaller and more qualified way than its authors first believed. And that, in a sense, is the more important cautionary tale, because it is the one that can happen to careful, brilliant, honest people. It is not a story about bad scientists. It is a story about how hard the truth is to pin down out here at the edge, where the only instrument that can reach the answer is also the only instrument that could fool you. What they did sounds bizarre when you say it plainly. They encoded a single qubit of quantum information into one cloud of entangled particles inside the system. Then they fired a carefully timed pulse between the two sides of that system, a particular kind of coupling that was meant to imitate something exotic, the negative energy that, in the equations of general relativity, could hold a wormhole open just long enough for something to slip through it. Then they waited, and then they saw it. A sharp peak rose in the data. The qubit of information had disappeared from one side of the system and reappeared on the other side. In the language of quantum information, that is teleportation, and by itself it was nothing new. Qubits had been moved across systems like that before. That part was ordinary. What was extraordinary was the interpretation the team placed on it. Let me take you into the room for the moment it happened, because it is worth feeling it the way they must have. The chip is cold and humming inside its housing. 9 qubits are carrying the experiment. The team has prepared the 2 entangled sides, fired the coupling pulse, and now they are watching a screen, waiting for the data to come back. For a heartbeat there is nothing to see, just the ordinary noise of a delicate machine. And then the peak appears, clean and sharp, exactly where the theory said it would be if a qubit had passed through the throat of a wormhole and come out the other side. In that instant, before anyone has had time to argue about what it means, it simply looks as though something impossible has happened in front of them. A piece of information has crossed the system in a way that the mathematics describes as a journey through curved space, into one black hole and out of another. The people in that room are looking at a screen and seeing, or believing they see, a fragment of gravity itself behaving inside a machine they built. It is the kind of moment a physicist waits an entire career for. The team was careful about the words they chose, and the words were remarkable. They were not claiming to have built a real wormhole in space. They knew they had not punched a hole in the cosmos. What they claimed was that the quantum system they had constructed was, in a precise mathematical sense, the same thing as a traversable wormhole, viewed from the other side of a profound correspondence between two kinds of physics. In their picture, the qubit had not merely been transferred from one place to another. It had fallen into a black hole on one side of a holographic universe, slipped through the throat of a wormhole, and emerged from a second black hole on the other side. They argued that they had seen not just teleportation, but the actual dynamics of a wormhole, reproduced inside 9 qubits on a chip. On the 1st of December that year, the result landed on the cover of the journal Nature, which is about the most prominent place a scientific result can appear. The press coverage was immediate and enormous. The New York Times wrote about it. The Guardian covered it. New Scientist, Quanta, and outlet after outlet carried the story. A press release from Caltech called it a first-of-its-kind quantum gravity experiment on a chip. For a few heady weeks, it looked as though physicists had finally done the impossible, had taken gravity, the one force that has stubbornly resisted every attempt to unite it with quantum mechanics, and coaxed a piece of it into behaving inside a laboratory device. It looked like the beginning of an entirely new kind of science, one where the grandest puzzles of the cosmos could be tested on a benchtop. And then, slowly at first and then all at once, the cracks began to show. Because other physicists had started reading the paper very carefully, and they had begun to ask a question the headlines had mostly raced past. The 9 qubits had certainly done something. But what exactly had they done, and did it have anything at all to do with gravity? Part 7. The Glasses. To understand both what the team claimed and what went wrong, you need to understand the single strangest idea in modern theoretical physics, the idea that made the whole experiment thinkable in the first place. It is called holography, and once you see it, you will never quite look at reality the same way again. Here is the claim, and I want to state it as plainly as it deserves. Some quantum systems, when you look at them in the right way, behave exactly like gravitational systems in a higher number of dimensions. Not approximately, not as a loose analogy, exactly. You can write down, on one side of a page, a cloud of particles bouncing around under the ordinary rules of quantum mechanics, with no gravity in the description at all. And you can write down, on the other side of the page, a black hole sitting in curved space, governed by Einstein's theory of gravity. And the mathematics will tell you that these two descriptions, which could not look more different, are secretly the same. Anything the quantum system can do, the gravitational system can do, and the other way around. They are two languages describing one reality. The simplest way I have found to picture this is to imagine a pair of mathematical three-dimensional glasses. Take the glasses off, and you're looking at a quantum system, just a swarm of particles interacting, doing quantum things, with no gravity anywhere in sight. Put the glasses on, and the very same system suddenly looks like gravity. Curved space appears, black holes appear, and if conditions are right, wormholes appear. Same physics underneath, two completely different pictures depending on whether the glasses are on or off. This idea has been with us since the 1990s, growing out of work by physicists including Gerard 't Hooft, Leonard Susskind, and most famously Juan Maldacena, whose 1997 paper turned the principle into a precise mathematical tool that thousands of physicists have been using ever since. It is one of the most productive and most baffling results theoretical physics has ever produced. To feel why holography is so startling, it helps to sit with the sheer mismatch between the two sides of the page. On one side, you have a quantum system living in a certain number of dimensions, with no gravity in it whatsoever, just particles and their interactions. On the other side, you have a universe with one extra dimension of space, complete with curved space-time and the full machinery of Einstein's gravity. Common sense says these should be entirely different physical situations. Holography says they are the same situation written in two alphabets. Every question you could ask on the gravity side has an exact translation into a question on the quantum side, and the answers always agree. It is as though you discovered that a sculpture and a piece of music were secretly the same object, that you could convert one into the other without losing a single detail. Physicists did not want to believe this at first. They believe it now because the translations keep working, again and again, in case after case, with a precision that leaves little room for coincidence. The particles in the SYK model have a name worth knowing, because it adds to the strangeness. They are Majorana fermions, named after the Italian physicist Ettore Majorana, who vanished mysteriously in 1938 and left behind, among other things, the prediction of a particle that is its own antiparticle. These are the objects the model is built from, and they interact not in tidy pairs but in tangled groups of 4, all coupled together in a random web. That randomness is part of what makes the model behave like gravity rather than like an ordinary material. And the property that seals the connection is the one we touched on, the saturation of the chaos bound. When physicists say a system saturates the bound, they mean it scrambles information at the absolute maximum rate the universe permits, no faster being possible. To picture scrambling, imagine writing a single secret on a slip of paper and dropping it into a churning crowd. At first, the secret is in one place. A moment later, it has been whispered and jostled and smeared across the whole crowd, no longer readable from any one person, though in principle still present in the chaos of the whole. Black holes do this at the maximum possible speed. The SYK model does too. And that shared, maximal scrambling is not a loose family resemblance. It is the precise mathematical signature that the two are, through the glasses, the same kind of thing. That is the thread the wormhole experiment was trying to pull on, and it is why the experiment was, in principle, such a beautiful idea, even before we ask whether it actually worked. The wormhole experiment lived entirely inside this idea. The quantum system the team used has a name. It is called the SYK model, after the 3 physicists who developed the pieces of it, Subir Sachdev, Jinwoo Ye, and Alexei Kitaev. The model describes a soup of particles, all interacting with each other in a particular random pattern. On its own, written out as raw quantum mechanics, it sounds dry and abstract, but the SYK model has a quiet, almost embarrassing feature. When you put on the holographic glasses, it looks like a tiny low-dimensional universe with gravity inside it. You can have black holes in there. You can, in principle, have wormholes. The SYK model is one of the cleanest known examples of the glasses actually working, a quantum system that genuinely speaks the language of gravity when you look at it correctly. What makes it such a trustworthy stand-in for gravity comes down to a property that sounds technical, but carries a strange beauty. It has to do with chaos, with how quickly a system scrambles information, smearing a single fact across all of its parts until it can no longer be read off from any one piece. In 2016, 3 physicists, Juan Maldacena, Douglas Stanford, and Stephen Schenker, proved that there is a maximum possible rate at which any system in nature can scramble information, a kind of universal speed limit for chaos, set by the temperature and by the fundamental constant that governs the quantum world. Nothing can scramble faster than this bound. And here is the haunting part. Black holes scramble information at exactly that maximum rate. They are the fastest scramblers the universe allows, and the SYK model, that abstract soup of particles, also scrambles at exactly the maximum rate. That is not a coincidence. It is the fingerprint of the gravitational connection. A system that scrambles information as fast as physically possible is, through the holographic glasses, the same kind of object as a black hole. The chaos is the tell. There is one more layer, and it is the layer that turns holography from a curiosity into something that touches the nature of space itself. In 2013, Maldacena and Susskind proposed a startling equivalence, often written as a short equation that reads ER equals EPR. On one side stands the wormhole, a bridge through space first described by Einstein and Nathan Rosen. On the other side stands quantum entanglement, the spooky connection that links 2 particles so that measuring one instantly tells you about the other, first sharpened by Einstein, Podolsky, and Rosen. The proposal says these 2 things, the wormhole and the entanglement, might be one and the same. Every entangled pair of particles in this view is connected by a tiny, untraversable wormhole, and the fabric of space itself might be woven out of countless threads of entanglement. If that is true, then space is not the fundamental stage on which physics happens. Space is something that emerges, knitted together out of quantum connections, and a machine that manipulates entanglement is, in a real sense, manipulating the threads of space. Pause on that idea, because it may be the most radical thing in this entire story, more radical even than the end of the universe. We're used to thinking of space as the stage, the empty container in which everything else happens, the most basic and unquestionable backdrop there is. The proposal hidden inside holography is that space is not basic at all. It is woven, stitched together out of countless threads of quantum entanglement, the way a fabric is made of threads that are more fundamental than the cloth. Pull the threads apart in this picture, and the space between two regions stretches and thins. Weave them tighter, and the regions draw close. Distance itself becomes a measure of how entangled two things are. If that is right, then the smooth, continuous space we move through every day is an emergent appearance, a large-scale pattern arising from something far stranger underneath. The way the smooth surface of water emerges from the frantic motion of molecules you cannot see. And that is why a wormhole experiment, if it truly worked, would be so much more than a curiosity. To send a signal through a wormhole by manipulating entanglement would be to reach down to the threads themselves and tug on the weave of space. It would be a demonstration that the dream is real, that the fabric of reality is made of information and can be handled as such. That is the prize that made 9 qubits on a chip feel, for a few weeks, like a turning point in the history of physics. It also explains why the negative energy was so central and so delicate. Ordinary matter and ordinary energy always pull a wormhole closed, faster than anything could cross. Only something exotic, a region where the energy dips below the emptiness of empty space, can hold the throat open, and such negative energy is rare and fragile and tightly constrained by the laws of physics. The whole experiment hinged on reproducing, inside a quantum system, the one ingredient that nature hands out most grudgingly. When you understand how much had to go right, and how subtle each piece was, you understand both why the claim was thrilling, and why it was so vulnerable to the question of whether the glasses had ever truly been on. The trick that turns all of this into an actual wormhole you can send a qubit through was worked out by Daniel Jaffris years before the experiment, in a paper with Ping Gao and Aaron Wall. They showed that if you take two quantum systems that are entangled with each other, you can couple them together in a very specific way that, on the gravitational side of the glasses, looks like a pulse of negative energy. And negative energy is the magic ingredient. Ordinarily, a wormhole, even if one existed, would pinch itself shut faster than anything could cross it. But feed it a pulse of negative energy, and for a brief moment the throat is held open, just long enough for something to slip through. The coupling pulse the team fired between the two sides of their system was the experimental stand-in for that negative energy shockwave. When they applied it, the qubit went through. And so, armed with all of this, the team argued that they had not merely seen teleportation. They claimed they had seen 5 specific things, 5 fingerprints, all of them signatures of how a real wormhole would behave. The information scrambled and thermalized the way it should when something falls into a black hole. The signal arrived with a small delay, the kind general relativity predicts for something crossing a curved region of space. The signals came out in the correct causal order. There was a pattern in the data they called perfect size winding, which they put forward as the clearest, sharpest proof, the smoking gun. And the coupling between the two sides matched what a negative energy shockwave would do. 5 fingerprints, all pointing in the same direction, all pointing at gravity. If they were right, it was the first time in history that a controlled laboratory experiment had reproduced a piece of gravitational physics, not by building a black hole, which they certainly had not done, but by building a quantum system that was supposed to be mathematically identical to one, viewed through the other lens. That was the claim. And the question that a group of physicists at Berkeley began asking, almost the moment they read the paper, was deceptively simple. Were the glasses really on? Or had the team only convinced themselves they were? Part 8. 3 people and a page of math. On the 15th of February 2023, 3 physicists at the University of California, Berkeley, posted a paper to the scientific archive that nobody at Caltech, Harvard or Google was going to enjoy reading. Their names were Bryce Cobrin, Thomas Schuster and Norman Yao, They were not outsiders taking a swing at a famous result for the attention. Yao runs a group at Berkeley that works on exactly this kind of physics, the place where quantum information and gravity start to blur into each other. These were people who knew the territory as well as anyone alive. That detail matters more than it might seem, because it shapes how you should hear everything that follows. This was not a rival group with a grudge, nor a band of skeptics looking to puncture a famous result for the sport of it. It was a laboratory whose own daily work lives in the same narrow borderland where quantum information and gravity meet. People fluent in exactly the mathematics the original team had used. When a group like that reads a startling claim, they do not reach first for doubt. They reach for understanding. They want to know how the thing works, to trace the machinery and feel the gears turn, and it was in the act of trying to understand the result sympathetically, from the inside, that the trouble surfaced. The most damaging critiques in science often come not from enemies, but from the colleagues who tried hardest to make sense of your work and could not. That is the immune system doing its job, and it is worth remembering that the people who took the wormhole claim apart were, in a real sense, the people who had taken it most seriously. When the Nature paper had come out, Yao and his students did what any careful research group does with a startling claim. They sat down to work out in detail how a model that small could possibly be doing what the headline said it was doing. 9 qubits, 7 particles in the simplified model, a mere handful of interaction terms. They wanted to understand the machinery, to trace exactly how the gravitational behaviour was supposed to emerge from so few moving parts. And as they worked through it, they found a problem, not a small one. To see what they found, you have to know one more thing about how the team had built their model. The full SYK model, the real one with all its gravitational complexity, is enormous. To get the gravity to truly emerge, you need a great many particles all talking to each other, and the mathematics runs into hundreds of interaction terms. No quantum computer in existence can run something that large, not Sycamore, not anything. So the team had to shrink the model down without breaking the parts that mattered. And the way they did that was remarkable in its own right. They used a machine learning algorithm to prune the model. They started with a full set of interactions and had the algorithm throw them away one by one, keeping only the ones that seemed to preserve the key wormhole signature, until they had a stripped-down version they called a sparsified model. By the end of the process, they had something tiny, 7 particles, only about 5 interaction terms pruned down from hundreds. That pruning step deserves a moment of suspicion in hindsight, even though at the time it looked like a clever solution to an impossible problem. The team had taken the full model, with its hundreds of interaction terms, and mapped those interactions onto the connections of a neural network, the same kind of structure that powers modern artificial intelligence. Then they trained the network to delete as many of those connections as it could, while still preserving the one wormhole signature they most cared about. Think about what that means as a method. You're not keeping the model honest by preserving its underlying physics. You're keeping the model honest by preserving a particular output, the very output you are hoping to measure. You're teaching the system, in effect, to hold on to the answer you want to see. There is nothing dishonest about this. It is a standard and powerful technique, but it carries a hidden danger, which is that you may end up with a model that produces the right-looking signal for reasons that have nothing to do with the physics you believe you're studying. You may sculpt a key that fits the lock without the key being made of the right metal. Bryce Coburn, Thomas Schuster, and Norman Yao were exactly the kind of group to notice that danger, because probing the boundary between quantum information and gravity is the daily work of Yao's laboratory at Berkeley. When they sat down with the sparsified model and asked what it was really doing, the room metaphor sharpened in their hands. A real black hole, recall, is a room full of people in a panic, every voice drowning every other voice until no single statement can be recovered. Information smeared everywhere. The sparsified model they found was the opposite kind of room. Its parts commuted, which is the technical way of saying they did not interfere with one another at all. Picture a room where everyone has agreed in advance to ignore everyone else, each person carrying out their own assigned task in perfect parallel, never colliding, never drowning anyone out. Such a room can look busy. It can even produce patterns that, glanced at from outside, resemble the churning of the panicked room. But the churning is not there, and a system that cannot churn cannot scramble, and a system that cannot scramble is not, through the holographic glasses, behaving like a black hole at all. The question was no longer whether the qubits had done something. It was whether the something they had done deserved any of the gravitational language that had been wrapped around it. Small enough to fit on 9 qubits, and, they argued, still faithful enough to the original to behave gravitationally. That was the object that had teleported a qubit. Not the full SYK model, but a machine-learned skeleton of it. When Kobrin, Schuster and Yao examined that skeleton closely, they found it had a specific mathematical property, and the property was damning. The simplified system was, in their words, fully commuting. You do not need the technical definition to feel the force of what that means. You need a picture instead. Think of a real gravitational system, a black hole, as a room full of people in a panic. Everyone is shouting over everyone else, bumping into each other, and within a few seconds it is total chaos. You could never reconstruct who said what, because every piece of information has been smeared across the entire room. That smearing is exactly what physicists mean when they say a system scrambles and thermalizes, and it is how gravity is supposed to behave at the quantum level. It is the panicked, churning room. A fully commuting system is not like that at all. A fully commuting system is more like a room full of people who have all agreed in advance to ignore one another completely. They can stand in the same room, they can each be doing something at the same time, but none of them interferes with any of the others. They simply carry out their own assigned motions in parallel, politely, without ever colliding. There is no panic, no churning, no smearing of information across the crowd, and that, the Berkeley group realized, was the kind of system the experiment had actually built. Not a panicked room that scrambles like a black hole, but a quiet room of people ignoring each other. The question was what that quiet room did to the 5 fingerprints, the 5 proofs of gravity the original team had been so careful to lay out. The answer, it turned out, was that it began to dismantle them, one after another, and the dismantling was about to become very public and very hard to argue with. Part 9. When the fingerprints fell. The dismantling came in 3 blows, and they landed one after another, each one falling on a different piece of the original case. Follow them carefully, because this is the moment the glasses came off. The first blow struck the very first fingerprint, the claim about scrambling and thermalization. The original team had listed it as one of the 5 signatures of gravitational behavior, the churning, smearing chaos that information undergoes when it falls into a black hole. But a fully commuting system, the quiet room where everyone ignores everyone else, does not thermalize. It cannot. The pieces do not interfere with each other in the chaotic way they would have to for that smearing to happen. The people in the room are too polite, too parallel, too independent. So that fingerprint, the Berkeley group argued, was not actually present in the experiment at all. It only looked as though it was. The system had produced a signal that could be mistaken for thermalization, but the underlying churning that the word is supposed to describe was simply not there. The second blow was aimed at the smoking gun, the one the original team had held up as the clearest proof of all, the pattern they called perfect size winding. This was supposed to be the signature that locked in the gravitational interpretation, the piece of data that could not be explained any other way. Kobrin and his colleagues showed something deflating about it. Perfect size winding, they demonstrated, is something that small, fully commuting systems do all the time. It is a generic feature of being small and being commuting, full stop. It has nothing in particular to do with gravity. Worse, it tends to vanish when you make the system larger, which is precisely the wrong behavior for a genuine signature of fundamental physics, which should become clearer, not disappear, as you scale up. So the single most important piece of evidence, the one the whole case had been built around, turned out to be a feature of the simplification itself. The act of shrinking the model down with machine learning had produced the very pattern that was then read as proof of a wormhole. This is a subtle and humbling kind of mistake, and it has a name, or at least a cousin with a name. Physicists sometimes call it the lamppost problem, after the old story of the man searching for his lost keys under a streetlight, not because he dropped them there, but because the light is better. You find a pattern in the place you happen to be looking, and you mistake the pattern for a discovery, when in truth the only reason you can see it is that the place you chose to look was lit in a particular way. The simplification that made the wormhole signature visible was also the thing that generated it. The keys were never under the lamppost. The light was just brightest there. It is worth lingering on why perfect size winding was supposed to matter so much, because its fall is the most instructive part of the whole episode. Size winding is a particular mathematical pattern in how a piece of quantum information spreads out, or grows in size, as it moves through the system. In a genuine gravitational setting, a specific, clean version of that pattern, the perfect version, is meant to be the fingerprint that a qubit has truly traversed a wormhole, rather than merely hopped across by some mundane route. The original team had pointed to it as the sharpest of their 5 signatures, the one piece of evidence that, more than any other, locked the gravitational reading into place. So when the Berkeley group showed that this same clean pattern shows up routinely in small commuting systems that contain no gravity at all, the loss was not of a minor detail but of the keystone, and the scaling argument made it worse. A real signature of fundamental physics should sharpen as you make the system bigger, growing clearer and more undeniable as you approach the regime where the duality truly lives. Perfect size winding did the reverse. It faded as the system grew, which is the telltale behavior of an artifact, something produced by the smallness of the model rather than by any law of nature hiding inside it. This is what makes the whole affair such a careful, uncomfortable lesson, rather than a simple story of error. Nobody had faked anything. The pattern was genuinely in the data. The qubit genuinely teleported. The mistake, if it even deserves so harsh a word, lived in the interpretation, in reading a pattern as proof of gravity, when the pattern was in fact a byproduct of the shortcut taken to make the experiment possible at all. That is a far more insidious kind of error than a faked result, because it cannot be caught by checking anyone's honesty, or by rerunning the machine. It can only be caught by someone willing to sit down and reason all the way through the model structure, which is precisely what the Berkeley group did. The reaction across the field reflected that subtlety. There was no scandal, no accusation, just a quiet and serious reassessment. John Preskill's measured remark that the evidence for a gravitational interpretation was weakening carried weight precisely because of how careful it was. And a blunter question began to pass between researchers, asked with real unease rather than mockery, about whether the whole young dream of doing quantum gravity in a laboratory had been pronounced alive too soon. Nobody had a tidy answer, and the absence of a tidy answer was itself the point. The third blow fell on the teleportation signal itself. When the Berkeley group looked closely at how the signal actually behaved, in detail, beat by beat, it did not match what you would expect from a qubit crossing a genuine traversable wormhole. The shape was off. The dynamics were wrong. The agreement that the original paper had implied between the data and the gravitational prediction was looser, much looser, than the headlines had suggested. The match was real enough to be suggestive, but it was not the clean, tight correspondence that a true wormhole crossing should have produced. 3 of the 5 fingerprints, then, were gone, or at the very least badly compromised. Notice how strange a kind of loss that is. The original case had been built like a structure resting on 5 pillars, and the argument was that even if 1 or 2 seemed shaky, the weight of all 5 together made the gravitational reading hard to escape. Pull 3 of the 5 away and the structure does not just lose some strength, it loses the logic that held it up. Because the remaining pillars were never meant to stand alone. What had looked like a convergence of independent clues, all pointing at gravity from different directions, now looked more like a single artifact of smallness, wearing several different disguises. That is the quiet devastation of the Berkeley analysis. It did not merely subtract evidence, It suggested that several pieces of what had seemed like separate evidence were really the same simplification, seen from different angles, mistaken for a chorus when it was only one voice in a hall of mirrors, thermalization absent, perfect size winding an artifact, the teleportation signal a poor fit. So, were the glasses really on? That had been the question all along, and now it had an answer that nobody especially wanted. For this tiny, machine-learned, fully commuting model, the glasses had never really been on at all. The team had looked at their quiet room of polite parallel particles and seen, reflected back at them, the curved space and black holes and wormhole throats they had spent years hoping to find. But the gravity they saw was not in the system. It was, at least in large part, in the looking. The mathematics that should have made the quantum system genuinely identical to a gravitational one only works when the system is large enough and chaotic enough to carry the duality, and this system was neither. The glasses had been sitting on the table the whole time. The reaction in the field was quiet, but it was unmistakable. John Preskill, a highly respected theoretical physicist at Caltech, who had not been part of either group, summed up the mood when he told Quantum magazine that he felt the evidence for a gravitational interpretation was weakening. That is, in the careful language physicists use, a strong statement, and a sharper version of the same worry was circulating among researchers in the field, a question asked half in earnest and half in dismay. Was quantum gravity in the laboratory dead? Had the whole dream of putting gravity on a chip died almost as soon as it was born? Nobody had a clean answer. The original team did not simply concede. They pushed back, and the argument did not end in a press conference or a retraction. It went somewhere stranger. It went into the slow, formal machinery of science, and it stayed there, unresolved, for 2 long years. Part 10. Bolted to the record. The original team did not roll over, and it would be unfair to suggest they did. They published a response, arguing that the commuting model still captured something meaningful, even if it was not the full gravitational jewel they had first described. Ping Gao, one of Jeffress's longtime collaborators, went further and proposed that what the experiment had simulated was a kind of pseudo-holographic behaviour. Not quite gravity, but not nothing either. Something in between, with its own teleportation mechanism, operating in a different regime than a true traversable wormhole, but still tied however loosely to the holographic ideas that had inspired it. The dispute, in other words, did not collapse into a simple verdict of right and wrong. It settled into the uncomfortable middle, into a fault line that runs through the entire holography program. That fault line is worth naming clearly, because it is the real intellectual stake of the whole affair. There is a difference between a system that is dual to gravity, exactly, mathematically interchangeable, the glasses fully on, and a system that merely mimics some of gravity's outputs under particular conditions. The first is a precision instrument, a genuine window into how gravity works. The second is a suggestive analogy, a thing that produces gravity-like numbers without being gravity in any real sense. The wormhole experiment, as the dust settled, appeared to sit somewhere between the two, and the field could not agree on exactly where. It was not a fraud. It was not a triumph. It was something harder to talk about than either, a result that had been oversold at the moment of its birth, and was now being painfully renegotiated in public. The middle ground that Ping Gao proposed is worth understanding, because it is where a lot of thoughtful physicists actually landed, and it is more interesting than either cheerleading or dismissal. His idea was that the experiment had captured something he called pseudo-holographic behaviour. The thought is roughly this: the full correspondence between the quantum system and gravity may not have been present in so small and so commuting a model, but that does not necessarily mean the teleportation was meaningless, or that it bore no relation to the gravitational story at all. There may be a kind of partial, shadow version of the mechanism at work, a teleportation that operates by related mathematics in a different regime, neither the full gravitational jewel nor a mere coincidence. It is the scientific equivalent of saying the photograph is not the scene, but it is not a random smear of colour either. It captures something of the shape, even if it loses the depth. Whether that is a profound insight or a face-saving hedge is, fittingly, still debated. That debate traces a fault line that runs through the entire program of trying to study gravity through quantum systems, and naming it clearly is the most useful thing this whole saga offers. On one side is a system that is dual to gravity exactly, mathematically interchangeable, the glasses fully and reliably on, every translation between the two languages holding without exception. Such a system is a precision instrument, a true window through which the workings of gravity can be read. On the other side is a system that merely mimics some of gravity's outputs under particular fragile conditions, producing gravity-shaped numbers without being gravity in any real sense. Such a system is a suggestive analogy, valuable for intuition but treacherous if mistaken for the real thing. The hard truth the wormhole experiment forced into the open is that it can be genuinely difficult, sometimes for years, to tell which of the two you are holding. And that difficulty is not a failure of any one team. It is a property of the territory, a sign of how far past our old certainties these machines have carried us. When nature took the rare step of bolting a formal counterstatement onto its own celebrated cover, it was not punishing anyone. It was admitting on the record that the line between the precision instrument and the suggestive analogy had turned out to be much harder to draw than the original excitement had allowed. And the 2-year gap between the headline and that admission is the part every scientist should remember, because it shows how the speed of a thrilling claim and the speed of its careful correction have come badly out of step. Then, in the middle of 2025, the journal Nature did something it does not do often. It published the Berkeley critique formally, as a peer-reviewed paper in a category called Matters Arising, printed alongside a reply from the original team. The original paper was not retracted. It is still there in the literature, still on the record as a published result. But now there is attached to it, formally, permanently, a statement from another set of physicists saying that 2 of the 5 gravitational fingerprints are not actually present, and that the third only looks present because of the way the model was shrunk. The team's reply, in essence, agreed that many of the processes their experiment ran on the learned model do not have a gravitational description, while maintaining that some of them still do. The journal had bolted a warning label onto one of its own most celebrated covers. It is hard to overstate how unusual that step is, and how much it should reshape the way we read a headline. Matters Arising is a category most people have never heard of, reserved for the rare occasions when a serious, substantiated challenge to a published paper is judged important enough to print formally alongside the original author's reply. It is not a retraction, which is a harsher and rarer act, reserved for results that are simply wrong or worse. It is something more nuanced, an official acknowledgement stamped into the permanent record that the meaning of a celebrated result is genuinely in dispute among experts. The original paper still stands, but it now travels through the world with a companion, a formal note from other physicists saying, in effect, be careful how you read this. For a journal to do that to one of its own cover stories is an act of institutional honesty that deserves respect, even as the need for it should give us pause. The system corrected itself on the record in public. It simply did so slowly, long after the first thrilling version of the story had already circled the globe and settled into the way people talked about what quantum computers can do. Think about the timeline of that, because the timeline is the real lesson. The result appeared on the cover of Nature in December of 2022. The careful refutation appeared on the archive in February of 2023, only a few months later. And yet the formal correction, the moment the scientific record itself was updated to reflect the doubt, did not arrive until 2025, more than 2 years after the headlines had gone around the world. For 2 years, the dramatic version of the story sat in the public mind, mostly uncorrected, while the careful version worked its way slowly through the machinery of peer review. The checking happened. The system, in the end, worked, but it worked at the speed of a journal, and the headlines had travelled at the speed of the internet, and the gap between those two speeds is where the trouble lives. And here is where I want you to feel the floor shift again, the way it shifted when we talked about the false vacuum, but in a different and quieter way. We started this story afraid of one kind of collapse, the physical collapse of a vacuum, a bubble of new reality erasing the old. But there is a second kind of collapse hiding inside this saga, and it may be the more unsettling of the two. It is the collapse of our ability to know when we have actually learned something. For the entire history of science, the deal we made with ourselves was that the truth might be slow, but it was reliable. Build the apparatus, run it again, and the errors would surface. What the wormhole story shows is that we have entered a territory where a celebrated result can be wrong, or half wrong, or wrong in a way nobody can quite pin down, and can stay standing for years, dressed in the full authority of the most prestigious journal in the world, while the correction crawls along behind it. The fear is no longer only that the universe might end. The fear is that we might lose our grip on the difference between a discovery and a beautiful mistake. And if you think that fear is confined to one experiment about wormholes, I have to tell you that it is not. Because the same crack was about to open under a completely different machine, doing a completely different thing in a laboratory on the other side of the world. Part 11. It was never only the wormhole. While the wormhole story was still going through its slow public unravelling, something else was happening quietly, in laboratories that had nothing to do with wormholes or holography at all. The same crack, the same uneasy question about whether we can trust what these machines tell us, was opening underneath other experiments, on other kinds of quantum hardware, aimed at completely different problems. And that is the moment a single controversy stopped being a single controversy and started looking like a feature of an entire era. Consider what happened in late 2025 at Swinburne University in Australia. A group there, led by researchers in the university's Centre for Quantum Science, developed a new technique for validating the outputs of a particular kind of quantum machine. The machine in question was a photonic quantum computer, one that does its computing with light, built to perform a specialized calculation called Gaussian boson sampling. You do not need the details of what that calculation is. What matters is what the new validation technique revealed when they applied it to a previous landmark experiment in that field, a result that had been celebrated as a milestone, a demonstration of quantum advantage, a machine doing something a classical computer supposedly could not. When the Swinburne team turned their new method on that celebrated result, they found errors, unexpected ones, errors that no one had spotted before, sitting inside a result the whole field had already accepted and moved on from. Let me be careful and fair here, because precision matters. The Swinburne result does not say anything specific about the wormhole experiment, and it says nothing at all about the false vacuum simulation. It is a different machine, a different problem, a different team. But it points at the same nerve, and it presses on it hard. Quantum computers are now routinely doing things we cannot independently check, and when we finally develop the tools to check them, we keep finding that the picture is messier than the headlines made it sound. The errors were there all along. They were simply invisible until someone built a new lens capable of seeing them. A little more about the machine in question will sharpen the point, because it shows how general the problem has become. Gaussian boson sampling is a task performed by a photonic quantum computer, one that computes using particles of light, photons, sent through a complex maze of optical components and then counted as they emerge. The reason anyone builds such a thing is that predicting the pattern of where those photons land is, for a large enough maze, believed to be effectively impossible for any classical computer, which makes it a natural candidate for demonstrating quantum advantage, the claim that a quantum machine has done something no ordinary one could. Several such demonstrations have been celebrated as milestones over the past few years. What the Swinburne team did was develop a new mathematical method based on a clever way of representing quantum states in terms of probability-like distributions, and then turn that method loose on the data from a previous landmark experiment. And the method found that the experimental output was, in important respects, far from the ideal that had been claimed for it, carrying errors that the original analysis had not revealed. The machine may still have outpaced classical simulation, but it had not done so as cleanly or in the way that the headline had suggested. Set the three stories side by side, and the shared shape becomes impossible to ignore. A wormhole that turned out to be mostly an artifact of a shrunken model. A boson sampler whose celebrated result hid errors no one had caught. And a false vacuum simulation that, however solid it looks, lives in exactly the same regime where independent checking is hardest. The thread connecting them is not fraud, and it is not incompetence. It is structural. We have built a class of machines whose entire value lies in going where classical computation cannot follow, and in doing so, we have walked out past the edge of the only verification method science has ever fully trusted. There is, encouragingly, a map of the way forward, and the people in this field are drawing it in earnest. It runs through machine-learned shortcuts that come bundled with provable guarantees of how faithful they are, so that no one is ever again fooled by a simplification that quietly manufactures its own answer. It runs through larger machines operated in regimes where several independent checks can be applied at once. A known classical limit here, a second theoretical description there, the hard constraints of symmetry somewhere else, so that no lone fragile signal has to carry an entire claim on its back. And it runs through a changing culture, a shift toward publishing not just the dramatic headline number, but the full diagnostic history of a result, every test it passed, and every way it might still be wrong, so that the next group is not left spending 2 years reverse engineering what was really done. It is slow, unglamorous work. It is also exactly how a powerful young science earns the right to be believed. And that is the pattern that should give us pause, not because any one experiment is fraudulent, but because the gap between what these machines can do and what we can verify they have done is real, and it is widening. Step back and look at the shape of the problem, because it is worth seeing whole. For most of the history of physics, there was a simple rule for telling a real result from a false one. You experimented, and then someone else experimented, and if the answers matched, the result was probably true. That rule still works for most of what scientists do, for telescopes and accelerators and chemistry and materials. But it is beginning to fail for quantum simulation, and it fails for a reason that is almost poetic in its inconvenience. The whole point of running a piece of physics on a quantum computer is to do something a classical computer cannot. So when the quantum machine tells you something surprising, you cannot turn to a classical machine to confirm it, because the classical machine's inability to keep up was the entire reason you reached for the quantum one. The verification you want is the verification you are structurally denied. This is the core of it. The same power that makes these simulations so useful is exactly what makes them so hard to trust. It is worth noticing how the wormhole was actually checked, because it tells you where the field has to go. The Berkeley group did not build their own wormhole. They did not run the experiment again on a second chip. What they did was take the mathematics the original team had used, sit down with it, and work through the consequences with what amounts to pencil and paper, and in doing so they found that the model was not doing what its builders thought. The decisive check in the end was not experimental at all. It was theoretical. 3 people reasoning carefully through the structure of a model found the flaw that no amount of rerunning the chip would have surfaced, because the chip would have happily produced the same misleading signal every time. That is a profound shift in how science polices itself. The correction came from understanding, not from repetition, and it came years after the fact in public, rather than quietly inside the peer review process before publication, the way such corrections used to happen. There is something almost familiar about this pattern, if you know the history of other fields. It has happened before, in other corners of science where powerful new computational tools arrived before the methods to validate them. Climate modelling went through it, in the decades when simulations of the atmosphere grew faster than anyone's ability to confirm that the simulations matched the real climate. Protein folding went through it, as algorithms began predicting the shapes of molecules faster than experiments could check those shapes. Economic forecasting went through its own version, models spinning out confident predictions that took years to test against the messy reality of actual economies. In every one of those fields, there was a stretch of time when the tool could clearly do something, but it took years of hard, unglamorous work to establish whether the tool was telling anyone something true about the world. The pattern is so consistent across those histories that it almost qualifies as a law. A powerful new way of computing arrives. It immediately produces results no one can check by older means. For a while, the field runs on a mixture of genuine progress and quiet faith, unable to fully separate the two. And then, gradually, the validation methods catch up and the community learns, sometimes painfully, which of its celebrated early results were real and which were artifacts of the tool itself. The discomfort of that catching up phase is not a sign that something has gone wrong. It is the sign of a field doing the necessary work of growing honest about its own instruments. Quantum simulation is simply in the thick of that phase now, and the wormhole story may be remembered less as a failure than as the moment the field admitted, out loud, that it had entered it. Quantum simulation may simply be living through its own version of that reckoning now, the awkward adolescence of a technology that has outrun the methods built to keep it honest. The encouraging part is that there is a way through, and the physicists working on this are not naive about it. The path forward involves tying the machine-learned shortcuts, the kind of sparsification that tripped up the wormhole team, to provable guarantees about how faithful they actually are, so that a simplified model comes with a mathematical certificate of how much it can be trusted. It involves running larger machines in regimes where several independent checks can be brought to bear at once, places where you can compare against a known classical limit, or against a second theoretical description, or against the constraints that symmetry imposes, so that no single fragile signal has to carry the whole weight of a claim, and it involves a cultural shift away from publishing only the dramatic headline result and toward publishing the full diagnostic history of a model, all the ways it was tested and all the ways it might fail, so that the next group does not have to spend 2 years reverse engineering what was really done. None of this is glamorous. All of it is necessary, and taken together, it is how a young and slightly wild branch of science grows up. Part 12. Signal and Artifact. So where does all of this leave us, standing as we are between two cold machines and two enormous questions? Let me try to gather the threads gently, the way you would gather them at the end of a long night. Picture the two refrigerators one last time, humming away on opposite sides of the planet. In a laboratory in Santa Barbara, a dilution refrigerator holds 9 qubits, the ones that teleported a piece of information across a system and were said, for a few bright weeks, to have opened a wormhole. In a basement in Germany, a different refrigerator holds 5,564 qubits, the ones that watched bubbles of true vacuum form and grow and collide, modelling the end of a universe in a ring of frozen wire. Both machines are chilled to within a hair of absolute zero. Both are doing something no human being has ever been able to do before. And in both places, physicists are using quantum systems to ask the universe questions that have never been asked inside a laboratory, questions about the shape of space and the fate of everything. Stand there in your mind for a moment, between the two of them, and feel how quiet it is. There is no drama in the rooms themselves, just the soft sound of cooling, and a stream of numbers, and a handful of people trying to decide what those numbers mean. The honest accounting is mixed, and it should be. The false vacuum experiment appears to be solid. Nobody has challenged it the way the wormhole was challenged, because the physics is more conventional, the model is well understood, and the qubits did what the equations said they would do. The bubbles formed. The dynamics matched the theory. The path to a 3-dimensional version is real, and people are walking it. That is genuine progress, a real enlargement of what we can study. I want to dwell for a moment on how unusual our vantage point is, because it is easy to rush past it on the way to the unease. You and I are alive at the precise hinge of this, the first stretch of time in which the largest questions there are, the architecture of space and the fate of the universe have started to become experiments rather than only thoughts. For every generation before ours, these were questions you contemplated and then set down, because there was nothing to be done with them but wonder. We are the first to be able to point a machine at them and watch a needle move. That is an extraordinary thing to be present for, and it would be a shame to let the legitimate worries about verification curdle it into mere cynicism. The right response to the wormhole story is not to stop trusting science. It is to trust it for the right reasons, to trust the slow correction rather than the fast headline, to admire a field that publicly bolted a warning onto its own most famous cover rather than quietly hoping no one would notice. There is a kind of maturity being learned here, in real time, and you are watching it happen. It is the difference between a child who believes every wonderful story and an adult who can hold a wonderful story alongside the patient question of whether it is true and love it no less for asking. The machines have given us a new way to listen to the universe, and the lesson of these few years is simply that we are still learning to tell the universe's own voice from the sound of our instruments reflecting back our hopes. That is not a reason for despair. It is the ordinary, difficult, honourable work of figuring out what is real, carried into a stranger and colder laboratory than any that came before. And the questions waiting at the end of that work are the most worthwhile ones a curious mind has ever been able to ask. The wormhole experiment is a different story, a cautionary one. The qubit really did teleport. That part was always real, and the data was always the data. But whether what happened on those 9 qubits had anything to do with gravity, in the way the cover of Nature suggested, is now an open question with serious doubt attached to it. The most honest summary anyone in the field offers is that the experiment showed something interesting, and that whether that something was a piece of gravity or just a clever and slightly misleading toy model is not yet settled. And underneath both, holding them together, is the question we planted at the very beginning, the one I asked you to carry. How do you know when a quantum simulation is showing you the truth? We have built machines whose entire reason for existing is to compute what we cannot, and in building them, we have arrived at questions whose answers we may not be able to independently confirm. Every sharp peak in the data now arrives trailing the same shadow of a question. Is this signal, or is it artifact? Is this the universe speaking, or is it the machine showing us a reflection of the assumptions we fed into it? The wormhole taught the field that the two can look identical for years. The Swinburne result hinted that the confusion is not rare, and the false vacuum experiment, solid as it seems, sits in the same new world as the others, a world where the instrument that takes us past the edge of the map is the only instrument that can read what is written there. This is the second meaning of the phrase we started with, and it is the one I want to leave you holding. We began by being afraid of the collapse of reality, the physical kind, a bubble of true vacuum eating the old universe at the speed of light, the floor turning out to be a ledge. That fear is real, and it is grand, and it may also be unimaginably distant. But there is a quieter collapse threaded through this whole story, and it is happening now, not in some far future. It is the slow collapse of our certainty about what is real, about when a result is a discovery, and when it is a beautiful mistake dressed in the authority of a famous journal. The most disturbing future is not, I think, that a bubble forms somewhere in the dark and undoes everything. The most disturbing future is the one where we finally point our machines at the largest questions there are, where we simulate the end of the universe or the structure of space and receive a clear, sharp answer, and we find that we have lost the ability to be sure whether the answer is true. That is a collapse of reality too, of a kind. Not the universe coming apart, but our grip on it. I do not want to leave you only with the unease, though, because the unease is not the whole of it, and it would not be honest to pretend it is. None of this means the field is broken. Holography is still one of the most powerful ideas physics has ever produced, and most theorists still believe that in some form the holographic principle is probably right. The SYK model is still a beautiful and useful thing. The false vacuum work is solid, and the people doing it are careful and clear-eyed. What has changed is not the science. What has changed is what physicists are willing to say out loud, and how carefully they are now willing to say it. A teleportation signal is not a wormhole, even when the mathematics whispers that it could be read as one. A pattern in the data is not a fingerprint of gravity just because someone has given it that name. A 9-qubit experiment run for a few seconds on a chip in California is not by itself proof that space is woven out of entanglement, however much a great many people would love it to be. The larger questions are all still open. We do not know whether the space we live in is fundamentally holographic. We do not know whether our vacuum is a true floor or a temporary ledge. We do not know whether the next generation of these machines will hand us real answers to those questions, or only more artifacts dressed up as discoveries. What we do know is this. Somewhere in Santa Barbara tonight, a refrigerator is humming with 9 qubits inside it. Somewhere in Germany, another is humming with 5,564. In both places, human beings are doing something nobody has ever tried before, using quantum machines to put questions to the universe that no laboratory has ever been able to ask. Sometimes the answers that come back are signal, the genuine voice of nature, faint and astonishing. And sometimes the answers are artifact, the machine handing us back a reflection of our own assumptions, dressed up convincingly enough to fool the best minds in the world for years at a time. Right now, in the strange cold centre of this new science, we're not always sure which is which, and maybe the most important thing we're learning, slowly and with some discomfort, is not any single fact about wormholes or vacuums or bubbles. Maybe it is a kind of humility. We are learning to listen to the universe through instruments we do not yet fully understand, aware at last that some of what we hear will be real, and some will be a trick of the listening, and that telling the two apart may be the longest and most important work still ahead of us. The machines are humming, the questions are the largest we have ever asked, and the answers, when they come, will be worth every ounce of the patience it takes to be sure of them.